All right, so it looks like I already have some of this done, which I do, but the problem is I apparently didn't hit the record button when I started doing this. So let's start over. Number 2, rewrite in radical form. So x to the 3/5 becomes the 5th root of x cubed. Number 4, again, we're just rewriting the form. So I'd have 7 to the 1/4. It would be x to the 6/4, but 6/4 reduces to 3/2, and then y to the 9/4. Number 6, I have the 5th root of 32. The 5th root of 32 is 2, and then 2 to the negative 1 is 1/2. Number 8, nothing I can do with the 24 and 4 because this has an exponent, so I'm going to clean this up. The square root of 4 is 2. 2 cubed is 8. Now I can take 24 divided by 8 to get 3. Number 10, same base, add the exponents. 3/4 plus 1/2 is 5/4. Number 12, I have 2 fractions and I'm multiplying, so I'm going to multiply across the top and across the bottom. So I have b cubed times c to the 1st over b to the 1/3 c to the 1/2. Then I have the same base, so I subtract my exponents. 3 minus 1/3 is 8/3, and 1 minus 1/2 is 1/2. Number 14, I'm going to use the rules from yesterday. I have the same index, so I'm going to write it as 1 fraction, and 64 divided by 4 is 16. 5th root of 16, there is nothing we can do, so we leave it just like that. Number 16, rewrite the form again. So 8 to the 1/5 becomes the 5th root of 8 in radical form. 8 to the 3/4 becomes the 4th root of a cubed. Number 20, again, rewriting the form. Square root of 17 becomes 17 to the 1/2. Number 22, I've got 5 to the 1/3, x to the 1/3, and then y to the 2/3. Number 24 is asking us to now evaluate. So the cube root of 27 is 3. Number 26, this is asking for the square root of 16. The square root of 16 is 4, and 4 to the negative 1 is 1/4. Number 28. Number 28, it says a women's regulation size basketball is slightly smaller than a men's. The radius of the ball that holds v cubic units of air is, and then it gives you this formula. And then for A, it asks you to find the radius of a women's basketball, and for B, it asks you to find the radius of a men's basketball. Well, this volume is written in the picture, so these become calculator problems. So I have 3 times 413 over 4 pi to the 1/3 power. And then for the men's basketball, I would have 3 times 455 divided by 4 pi to the 1/3 power. So for a women's basketball, it's 4.62 inches. And then for the men's basketball, it's 4.77 inches. All right. Number 30. Simplify. So same base, add the exponents. These would both be in 15ths. So this would be 5/15, and this would be 6/15, I'd multiply by 5 over 5, and I'd multiply by 3 over 3. So if I add them, 6/15 and 5/15 add to 11/15. Number 32. I have 1 over b to the 3/4, but we can't leave a fractional exponent in the denominator. So I'd multiply by b to the 1/4 over b to the 1/4. So I'd have b to the 1/4 over b. 34. I have different indexes. So 81 is 3 to the 4th. So I'd have 3 to the 4/8, but 4/8 is the same as 1/2. And this would be 3 to the 1/6. I have the same base, so now I can subtract 1/2 minus 1/6 is 1/3. I'd have 3/6 minus 1/6 is 2/6, and 2/6 is 1/3, but I started as a radical, so I would want to write my answer as a radical. 36. 25 is 5 squared, so I actually have 5 squared x squared to the 1/4 power. So I'd have 5 to the 2 times 1/4 is 1/2, and then 1/2 times 1/4 is 1/2. So this would simplify to the square root of 5x. And again, I started with a radical, I should end with a radical. Number 38, I have 2 terms, so I have to rationalize the denominator, so I have to multiply by the conjugate. I have to FOIL on top and on bottom. So I get h plus h to the 1/2 plus h to the 1/2 plus 1 all over h plus h to the 1/2 minus h to the 1/2 minus 1. And so that cleans up to h plus 2h to the 1/2 plus 1 all over h minus 1. And now that does not violate any of the rules. Number 40. Find the area of the triangle. So area is 1/2 base times height. The base of the triangle is 3 r to the 1/2 w to the 1/4. And the height of the triangle is 4 r to the 1/4 w to the 1/2. So 1/2 times 3 times 4 is 6. R to the 1/2 times r to the 1/4. I add the exponents. 1/2 plus 1/4 is 3/4. And then 1/4 plus 1/2 is, again, 3/4. And since this is area, I'm just going to say units squared. Number 42. Find the simplified form of this. So if it helps you, let's change this to radical form so you can see it. So 18 would be the square root of 9 times the square root of 2, which is 3 square roots of 2. This is the square root of 2, so I'm going to write that as 1 square roots of 2. And then this is the square root of 32. So 32 is 16 times 2, or 4 square roots of 2. So those are all simplified to square root of 2. So 3 plus 1 plus 4 is 8. So I have 8 square roots of 2, but exponent, I'm going to change that to exponential form. So I have 8 times 2 to the 1/2. Oh, and I just caught a mistake. Look at that. That was a negative. Minus. which now makes it even easier. It's just 0 because I have 4 square roots of 2 minus 4 square roots of 2, and I get 0. I'm glad I caught that. All right, number 44. Same base, add the exponents. And I already have a common denominator. 7 fourths plus 5 fourths is 12 fourths. 12 fourths is the same as 3. So that one's a pretty easy one. 46. Power to a power and multiply. 3/4 times 1/3 is 1/4. 48. So 64 is going to be 2 to the 6th power. So what I'm going to do is I'm going to write this as 2 to the 6th to the 1/4. Power to a power, I multiply, and I get 2 to the 3/2. So I can write that as the square root of 2 cubed, but as a square root, I'd want to write that as the square root of 4 times the square root of 2, because that would be 8. And I would get 2 square roots of 2 as my final answer. That one's a tricky one. A person could have said that 2 to the 4th power, and you could have simplified that, but then you would have had this to simplify. You would have had the 4th root of 4 that you would have had to simplify. So there's more than one way of doing that problem. Number 50. Negative exponent. Rationalize the denominator. Multiply by d to the 1/6 over d to the 1/6, because 5/6 plus 1/6 is 1. I cannot have fractional exponents or roots, radicals, in the denominator. So that is my final answer. Number 52. Okay. 52 says, a population of 100 deer is reintroduced to a wildlife preserve. Suppose the population does extremely well and the deer population doubles in 2 years. Then the number of deer after t years is given by d equals 100 times 2 to the t over 2. How many deer will there be after 4.5 years? So I have 100 times 2 to the 4.5 divided by 2. So there's going to be about 476 deer. We'll round to the nearest whole number. Part B says make a table that charts the population of deer for every year for the next 5 years. So to do this faster, I'm going to come in here. 100 times 2 to the x divided by 2 power. And then I'm going to go to my table. So for the first year, I would have 141. Second year, I would have 200. Third year, I'd have 283. Fourth year, I'd have 400. And fifth year, I would have 566. 52C, graph that. So I'm going to start at 0, because when we start at 0, it would be at 100. At the first year, it would be at 141. Second year, 200. Third year, 283. Fourth year, 400. And fifth year, 566. And essentially, it's implying that it continues on. And that's what they talk about in Part D. Using your table and your graph, decide whether this is a reasonable trend over the long term. What they're asking is the deer population going to continue to increase exponentially? And I would say this is not possible. there are too many other factors in nature that would affect this. All right, number 54. Another rationalizing the denominator. So I'm going to multiply by g to the 1/2 minus 2 over g to the 1/2 minus 2. And distribute on top. So I get g cubed minus 2g to the 5/2. And then when I FOIL the bottom, I'd have g minus 2g to the 1/2 plus 2g to the 1/2 minus 4. So then that would simplify to g cubed minus 2g to the 5/2 all over g minus 4. 56. Same base, subtract the exponents. This would be 8/10 minus 5/10, which would be 3/10. All right, I'm going to change these things. This 36 is 6 squared. So I'm going to write this as 6 squared, h squared squared, and j squared squared. These are all going to be squared, and these are all going to be to the 8th. So this is the 8th, 8th, 8th. So I get 6 to the 1/4, h squared to the 1/4, and j, sorry, this last one's a j, j squared to the 1/4. So these all should be the same. So I can write this as the 4th root of 6 h squared j squared. If you have it as a radical, unless they tell you to change the form, you should still leave it as a radical. Now, if you argue that this should be the 4th root of 6 times the square root of h times the square root of j, and you said, nope, I'd rather write this as the 4th root of 6 times the square root of h and j, I would give you 100% credit for that as well. Okay? All right. 256 is 2 to the 8th. And then this is a square root and a 4th root. So I have 2 to the 8th to the 1/2 to the 1/4. So 2 to the 8th to the 1/2 to the 1/4. Power to a power to a power. I multiply all those. 8 times 1/2 times 1/4. And I get 2 as my final answer. 62. I need to rationalize the denominator. This is just like a problem from yesterday's assignment. So I would have to multiply by the cube root of z squared to rationalize the denominator. So I'd get x, y, cube root of, z squared all over z as my final answer. And one more, and this one totally is different than a lot of stuff. It's a very good problem, but it actually has to do with factoring. When you have these, if you tried to multiply by the conjugate, it doesn't work, okay? But if you look on top, there is an x to the 1/3 in common. So I'm going to factor out an x to the 1/3, and I'm left with x to the 4/3 minus z to the 4/3. And I don't know if you can recognize it or not, but x to the 4/3 minus z to the 4/3 is the difference of squares. So that can factor into x to the 2/3 minus z to the 2/3 times x to the 2/3 plus z to the 2/3 all over x to the 2/3 plus z to the 2/3. And if you look, it has those in common, so those cancel. And then I'm going to distribute that, and I'm left with x minus x to the 1/3 z to the 2/3. That's a really good problem that involves last chapter and this chapter with rational exponents and with factoring.